If you are not very familiar or comfortable with looking at results of time frequency based analyses, it might initially seem a bit intimidating or confusing how to interpret all these different features, all these different colors and dimensions. And so here I'm going to introduce you to kind of how to think about or how to look at results of time frequency based analyses. Lest you think that this is a kind of a patronizing lecture, then let me assure you that these 5 steps that I will introduce you to are exactly the steps in the same order that I use every time I'm looking at time frequency results, whether they are from my own data analyses or if I'm reading a paper or reviewing a manuscript. So here is the 5-step plan. Step 1 is to determine actually what is even being shown on the plot. Generally, the most typically shown feature of the data to show in time frequency plots is power. This is the intensity or the strength of the frequency band specific activity over time. But people will also show connectivity results or correlation with behavior or all sorts of things. So it's important to make sure you know actually what feature of the data is being shown in the plots. That's the first step. Step 2 is to inspect the ranges and the limits of the plot. So what is on the x and y axes? Most of the time, the x-axis shows time, and most of the time, the y-axis shows frequency, but that's not necessarily the case. For example, sometimes, particularly in studies of intracranial recordings where they have laminar electrodes that go through the cortex, the y-axis might actually show depth of the cortex and not frequency. So it's important to inspect the axes and make sure you know what is being plotted. What is the color limit or the grayscale intensity? This is related to what is being shown. It could be that the color refers to power, but it's important to determine whether it's absolute power or power relative to a baseline, and so on. And then you want to have a quick look around inside the plot and see if any activity seems to be cut off on the edges or maybe saturated by the color limits, so you can't really get a full picture of what's going on in the plot. Okay, step 3 is to look at the results. One of the things you want to look for is to see if the results are distributed in time frequency space or if they are more localized. So this will help you in interpreting the results. And I'll give you some examples of what I mean by this on the next slide. You should understand what is the subspace of the total time frequency analysis that is being shown in the plot. If it's a time frequency power plot, it's likely that they're showing only the results from one electrode, or maybe they're showing only from one frequency or only from one time window. And this is not necessarily that the authors are trying to fool you or trying to manipulate you into only looking at a tiny piece of their data. It's unfortunately simply the case that time frequency based analyses deliver a very large and high dimensional space. And as we'll learn in the future, it's actually quite common to have something like a 5-dimensional hypercube of results. And we humans are generally not very good at viewing or interpreting these kinds of large dimensional spaces. And so we have to take slices of these spaces. So it's fine, but there should be some kind of justifiable motivation, either based on theory or based on previous literature or based on some characteristics of the data that motivate the authors only to show the results from one electrode, for example. So this is part of looking at the results. Then step 4 is we try to link the results to the experiment design, assuming that there is some kind of a task. You want to know what is happening at time 0. Is it a stimulus that came on the screen, or an auditory stimulus, or a button press or some kind of response? Are there multiple task events? And how are these represented or shown in the time frequency plot? And finally, step 5 is to try and understand the statistical procedures that are shown in the plot. So, for example, is there any statistical thresholding at all? Maybe there is no statistical thresholding, in which case the analyses should be considered qualitative rather than quantitative. If statistics were performed at every time frequency pixel, are multiple comparisons issues addressed? Are the analyses more geared towards data exploration, or are they more hypothesis driven? We will discuss these differentiations in the future when we talk about statistics, but these will change the how you interpret the results. Okay, so here's the 5-step plan. Now let's see how this works in action. So here we have a time frequency plot, and now we're going to go through these 5 steps and just sort of inspect this plot. So step 1, determine what is being shown in the plot. Here we see it's very clearly written in the title. This is decibel converted time frequency power. And we don't know what electrode is being shown here, but I happen to know that it's electrode FCZ, which is a frontal central electrode. And we can see these are, so we don't know exactly what the baseline period is, but presumably it's somewhere around here. Here you can see the color values, so it's symmetric. It goes from -3 to +3 decibels relative to baseline. Okay. Inspect the ranges and limits of the plot. So we see some of the baseline activity, which is nice. Here's time 0. It goes up to 1,000 milliseconds. And we get frequencies from maybe like 2 or 3 hertz up to around 40 hertz. And we can see that a lot of the main time frequency dynamics are contained within this time frequency window. There do appear to be some features that are sort of leaking out, outside into the into higher frequencies. So it's possible that there is some higher frequency dynamics that we are just missing in this plot because it only goes to 40 hertz. But so that's not really clear. There might be something here as well, but this is possibly, if this is a sort of fast experiment design, this might actually be the beginning of the next trial. So, step 3, look at the results. Here we see quite a few interesting features. So there's this kind of longish theta response increase relative to baseline, and it appears to be flanked by these 2 sort of bursts of upper alpha, somewhere around 10 to 15 hertz. And then, of course, there's this very prominent beta band suppression from 20 to around 30 hertz or so. And this seems also to come in beats. And actually, it looks like there's maybe even a little something happening before stimulus onset. Okay. So now we link the results to the experimental design. I happen to know that this plot came from an experiment that was that involved cognitive control and response conflict, and in this literature, it is very typical to see theta increases after stimulus onset and corresponding roughly to the time of the response, which could be somewhere around 500 or 600 milliseconds. So this seems to fit very well into what I know about this experiment and what I know about this literature. These other features are, maybe, these may or may not be sort of relevant, but, we want to kind of keep these in mind. The reaction time, the average response time, is somewhere generally around 500 or 600 milliseconds, and so some of these dynamics might be related to the response rather than to the stimulus per se, although it's a little bit difficult to tell exactly from this plot, just based on this plot, because we don't see the response locked plot. And finally, statistical procedures. Actually, there are none. I see no contours. There's no kind of boxes drawn around. So we don't know exactly what is and is not statistically significant in this plot. And so we just interpret this as a kind of qualitative glimpse of the landscape of activity here, rather than knowing exactly what can be statistically evaluated. Okay, so that was the 5-step plan, and this is really what happens inside my head when I first look at time frequency results. Of course, I do it a little bit faster in my head compared to now when I'm introducing it, but if you are new to time frequency based analyses, I recommend going through these stages in order to understand what's being shown to you. So one of the things that people often use time frequency based analyses to make inferences about is neural oscillations, brain oscillations. And so there is a debate that keeps coming up in literature about whether these findings actually reflect neural oscillations. And the issue here is that, or the question is, whether a feature that you see in time frequency space necessarily corresponds to an oscillation in the way that we understand neurophysiological oscillations to occur. In large part, this argument arises because of a feature of the Fourier theorem. So this, I presume, is a picture of Joseph Fourier, at least according to Wikipedia. This is what he looked like. We will discuss later that the Fourier transform is actually quite a remarkable and powerful data analysis technique. But what the Fourier transform what the Fourier transform does is allow us to represent any signal using a combination of sine waves and basically oscillatory processes. One of the sort of curious features of the Fourier transform is that it does not require that the signal is oscillatory or even periodic. The Fourier transform, as we will learn in the future, is a perfect representation of any signal. So this is Fourier giving his evil laugh here, because this the data do not necessarily need to exhibit oscillations in order for us to get results that can be represented in a time frequency power plot. So in this debate, if someone asks you about this, is this really a neural oscillation? Can you interpret this signal, this feature in your time frequency space as a neural oscillation? I think it is very important to make a clear distinction between two orthogonal questions that are two orthogonal issues that are often confused in this discussion. One question is, are time frequency based analyses useful in analyzing EEG and LFP and MEG data? And a second question, which I think is really orthogonal, is totally uncorrelated with the first question, is an interpretation of a neural oscillation appropriate in this particular case? So let me just address these two questions very briefly. There are a few disadvantages of time domain analyses, including that any activity that is jittered or non-phase locked, these dynamics are lost, they are invisible. There are very limited analysis possibilities, such as connectivity, cross-frequency coupling. Event-related potentials or time domain trial averaging often has low signal-to-noise and low statistical power, particularly for the later, more cognitive or associative components, so things happening after around 150 or 200 milliseconds. This is actually not a mathematical requirement or necessity, but empirically this tends to be observed. Furthermore, the sort of biophysical or physiological mechanisms that produce ERPs, particularly the later ERPs, are relatively unclear. Now we can contrast these disadvantages with advantages of time-frequency-based analyses. It allows you to interpret your results in more neurophysiologically meaningful ways, as I'll get to in a minute. And it provides a very flexible framework for many types of analyses, not only time frequency power, but phase dynamics, connectivity dynamics, frequency coupling dynamics. There are many so-called low-hanging fruits. This means that there are many aspects of brain function and cognitive function that are yet to be sort of fully charted with time frequency based analyses. So this is useful if you are trying to make a niche in some literature and make some new discoveries. Time frequency based analyses are also very amenable both to strict hypothesis testing and also to kind of open exploratory data analyses. So this is an advantage. And of course, they also produce very nice colored plots. That is not really a scientific advantage, but that's okay. So these are all arguments for using time frequency-based analyses in addition to or instead of time domain only analyses like event-related potentials. And all of these, except I guess for this one, but these have nothing whatsoever to do with interpreting your results in a framework of neurophysiological oscillations. These are entirely about having a rich information-packed signal, and we want to extract, or we are using time frequency-based analyses to extract more information than what we can get from event-related potential analyses or time domain analyses. So this is an answer to orthogonal question number 1. So now let's get to orthogonal question 2. Is it safe, or how confident can we be about interpreting a feature in a time frequency plot as a neural oscillation? Here, the issue is that the term oscillation in the context of neuroscience, in the field of neuroscience, is kind of a loaded term in the sense that there are a number of studied and understood biophysical mechanisms that produce periodic dynamics in neurons and in populations of neurons. And so when we are measuring at the macroscopic scale, even with an LFP, so even with a microwire that you just is inserted into the brain, but it then is low-pass filtered to extract sort of lower frequency components, this is a pretty macroscopic signal relative to the biophysical dynamics that produce oscillations. So that is the issue of interpreting features of time frequency analyses as neural oscillations. In my opinion, this boils down to the distinction between a manifest variable and a latent construct. So there are things that we presume are happening in the brain, and these are neural oscillations. And then there is the thing that we actually measure. So we cannot directly measure all components of all neurons, so it's difficult to really determine with 100% certainty that this thing that we see is an oscillation. But so we do the best with the thing that we can see, which is the manifest variable. So interpreting a feature of a manifest variable in the framework of a latent construct that you have some theoretical motivation to make this link. This is actually very similar to many other relationships between manifest variables and latent constructs that we see in psychology, in sociology, and definitely in cognitive neuroscience and in neuroscience more generally. So one might also ask the question, is the fMRI bold response neural activity? Or is a condition difference in reaction time something called attention, a cognitive state called attention? In all three of these cases, we have a latent construct. So we have something called neural activity. We have something called attention, a cognitive operation called attention. And then we have the manifest variable, which is the bold response or reaction time, or an EEG time frequency feature. And so I think this is the best way to think about this question. Can we interpret a feature of time frequency results as reflecting a neural oscillation? Yes, to the extent that we treat these as manifest variables. These are measurable things in the world, and we use these in order to make inferences about something that is more difficult to measure directly.